Good morning, everyone. I welcome you to this talk series, CS Katha Barta, where we invite academics and professionals to deliver their talks. Our guest for today's talk is Dr. Thiparat Chotibut. Dr. Chotibut is a theoretical and computational physicist at Chulalongkorn University, working on intersection of computer science and physics. He received his master's and PhD in theoretical physics from Harvard University and is currently leading the Chula Intelligent and Complex Systems Research Unit. He is also a Chief Global Officer and co-founder of Quantum Technology Foundation, Thailand. His work involves formulating and developing theoretical concepts and computational softwares to solve problems in science and mathematics, with the current focus on analysis and the design of novel ML algorithms through the lens of computational neuroscience, statistical physics, and many body quantum physics. Today, he will be speaking on topics from explainable NLP to quantum dynamic predictions. I welcome you, Dr. Chotibut, to CS Kathavarta. I invite you to take the virtual stage and begin your presentation.
All right. Thank you so much for the kind introduction and invitation to give a talk here. So this is my first time to give a talk to Indian crowds. So if you have any questions, please feel free to interrupt anytime. And today I would like to tell you a bit about my recent work that explore the intersection of temporal machine learning models and quantum many-body physics. Some people might have questioned how are there interactions between the two fields. But in fact, in this talk, I would like to highlight that, in fact, the synergy between many-body quantum physics and explainable natural language processing is quite natural. And at the same time, you can apply tools and models from temporal machine learning models that have been extremely successful for machine learning tasks, such as language modeling and time series prediction, to also solve some hard to simulate many body quantum physics problem. So the synergy is two sides. You can apply tools and techniques well developed in many body quantum physics side, which is shown and pictured, depicted by the picture on the left here. I asked ChatGPT to spit out the picture of many body quantum physics and use that and as a way to convince you that AI has become successful and that by using AI, you can solve interesting problems in many body physics. And also you can apply this many body physics to shed light into interesting explainable phenomena in recurrent neural networks, for example. So I would like to first introduce you to my university. I'm in Chulalongkorn University in Bangkok, Thailand. It's in downtown of Bangkok. And my office, which is located on the top floor of this building, overlook this beautiful view. So if you guys have any chance to visit Bangkok, please let me know. So my lab, Chula Intelligent Complex System, investigate in particular the emergent phenomena of interacting microscopic constituents when they combine into multiple number of them and emergent phenomena arises. One of the prototypical example is, of course, intelligence. How do intelligence arise from interacting neurons, for example? And today I would like to tell you about the synergy between the two fields of many-body quantum physics, which is also quantum complex systems, and recurrent neural networks in the first part. I'd like to tell you that the techniques from many-body physics somehow enable you to look into how inner working of RNN works, in particular in sentiment analysis task. And on the second part of the talk, I would like to tell you about an application of a modern machine learning models known as reservoir computing as a way to solve some hard to simulate many-body quantum physics problem, which I'll tell you in details later. Without further ado, I would like to start with the first part. So how do we use many-body quantum physics knowledge and tools to look into the inner working of recurrent neural networks? I probably don't have to motivate much because this is the CES community, and you all know that AI has been particularly successful in modern industry. However, in 2017, Ali Rahimi gave a test of time talk that tells the computer scientist and AI scientist audience that machine learning, even though it has been extremely successful, the practice of it is almost like an alchemy in the sense that there are many neural architectures and different architectures are good for different things. But if you ask why certain architecture is good for certain things, it's just really hard to be able to explain. And as a result, AI scientists back then performed trials and errors, try all the new architectures, and if it works, then you report in the proceedings, and it becomes widely adopted if that new architecture turns out to be beating the state-of-the-art benchmark data set. So this kind of sounds like an alchemic practice in the old days when people mix different elements together, and if you discover something useful, then it becomes useful, but you cannot ask the question why it is useful and then how does it work and how do you get to those useful elements. Similar to AI in six or 7 years ago, now there's become more and more effort to investigate how to explain or make AI more transparent, and that would be the focus in the first part of my talk. Specifically applied quantum many-body physics to look into the inner working of recurrent neural networks in sentiment analysis task, which is the prototypical task for language modeling. So let me start by motivating you what kind of mathematical architecture or computation will be concerning when we talk about language modeling. So the typical statistical sequence modeling framework is that you have a sequence of vectors, in this case, words, and from the sequence of vectors or words that you have seen from left to right or from early time to late time, you build a conditional probability distribution so that you can guess what is the probability of the next element or the next word. In this case is if your neural networks or your brain has read many English texts, you presumably will fill in this question mark blank as you, because I love, potentially you is the most frequent word you have seen in the past. And by this way, by using past training data of how you have read many past texts, English texts, you'll be able to build a representation of this conditional distribution and guess what is the likelihood of the next word. And then you pick the next word that is most likely based on the sequence of the past words that you have seen. In sentiment analysis task, it's still a conditional distribution in a sense that you have a long review of movies or products, and by these long reviews of movie and products, rather than having human to assign the probability that this review is good or bad, sometimes you build a computer program to read the statistics of what sequence of the review and assign the probability to a value of sigma. Sigma would be +1 with probability close to 1 if the review is good. And if the review is bad, probably the sigma would be -1, would be close to 1. Even though this kind of paradigm has been extremely successful, and large language model, ChatGPT, and the variants of it has become extremely useful based on this statistical sequence modeling, the inner working of the models, as complex as transformers, sometimes it's really hard to be explained and looked into. So it lacks explainability, even though it has performed miraculously well in terms of language modeling. On the other hand, I would like to draw some parallels for those of you who don't know much about many-body quantum physics. So in many-body quantum physics, we look into the microscopic quantum degree of freedoms of particles. In the simplest case, you can think of each particle, such as electrons, has an intrinsic degree of freedom called a spin. The spin can be either in +1 or -1, up or down direction along the z-axis. And by aligning the spins on a one-dimensional chain, there are ways that physicists have investigated what is the question, for example, what is the probability that if you have seen the spatial arrangement of the spins on the left of your system to be on certain configuration, what is the probability that the right of the configuration is spin up or down? And there are many well-known methods that are well developed to study this kind of correlation in the intrinsic degree of freedom, in this case depicted as a one-dimensional spin chain. Techniques well known such as matrix product states, tensor network, or density matrix renormalization group has been developed in order to look into how the correlation in this microscopic world of many-body quantum physics can be studied. Another paradigm, another task that machine learning has been extremely useful in many-body quantum physics is classification of phases of matter. If all your intrinsic degree of freedom of spin points in the same direction, then they will become magnetized. And in physics, we say it is ferromagnetic phase when this microscopic degree of freedom all form one directional pointing of this local degree of freedoms. We say it has a ferromagnet phase. The question is then, if you have a gigantic set of these particles and they are pointing up and down in certain ways, can you use machine learning models to look into this correlation or configuration of the spins and ask, is it in ferromagnet phase, or is it in paramagnet phase, or is it in some other phases of matters? And this sounds a lot like sentiment analysis in a way, because you have seen a large configurations of your variables and you try to assign certain probability to that class of configurations. And while the sentiment analysis and next words prediction are somewhat lacking explainability, interpretability, because the models that used to build this conditional distribution is based on recurrent neural networks mostly. And due to intrinsic nonlinearity, it is quite difficult to analyze the correlation in time, for example. On the other hand, if you look into this side, it sounds a lot like it. You try to assign probability to the configuration that you observe your particle system. And in this case, you're trying to assign the class of the configuration that you see. However, the tools and techniques on this many-body quantum physics is quite well developed, and there are some technical and theoretical tools that we can adopt to look into the inner correlations between the systems. So I'd like to tell you a mapping that enables you to convert one type of recurrent neural networks applied in particular to a task of sentiment analysis that can be converted into this quantum many-body physics language. And then we use tools called entanglement entropy as a way to look into the correlation in time in RNN. And I'll tell you the nature of sentiment analysis model that arise. Okay, let me tell you the mapping between the simplest case of recurrent neural networks or the shallow recurrent neural networks. So for what you're seeing here is the depiction of the time series computation in the translational invariant recurrent neural networks. So at each time step, the recurrent neural networks would take two inputs. One is the current words, which is applied by the fully connected layer input neurons. Each word xi will be mapped into a high-dimensional vector phi by a word embedding. Phi is a word embedding here. So you embed a word into a vector in high dimension. And there are some choices of the word embedding that make your words become more meaningful, which I'll discuss later. But this translational invariant RNN takes two inputs. One is the current time step word, and the other one is the previous time step that comes from the nonlinear computation of the RNN in the previous time. And then you keep repeating this computation for, until you reach the last word that you want to start to make prediction of this whole sequence. And when you read the last word, the output is a number C, which parameterizes the probability distribution, in this case, the conditional distribution we are trying to estimate. Is it a good or a bad review? If it's a good review, then this sequence of word will output the probability close to 1. If it's a bad review, then C will be, the probability will be close to 0. So C will be computed by the sigmoid activation function. So it will be close to 1 if it's a good review, and will be close to 0 if it's a bad review. Okay. Typically, this vanilla or shallow RNN is computed by many types of nonlinear rules, F. Typically, this is what make RNN computation hard to be analyzed because it's highly nonlinear. However, there's a special recurrent arithmetic circuit activation function which turned out to be quite useful and easy to train. It has nonlinearity. At the same time, it's not too nonlinear that we cannot analyze anything. In fact, by using this Hadamard product between the two inputs, so A Hadamard product with B, the ith element of this, it's just AI times BI. By using this quadratic nonlinearities, you can show that it has an exact mapping to a class of many body quantum states called matrix product states. You can see there are some analogies here of each block of the computation will correspond to, in this case, a tensor of rank 3. Each of the notation here of the circle with 3 legs are tensor of rank 3. And then when you concatenate the two tensor together, it means that you sum over the repeating index that leg specifies. This is the representation pictorially of that kind of computation to convince you that, in fact, the two computations between recurrent neural networks with this particular types of activation function is equivalent to what physicists call the matrix product state representation of many body quantum physics. Okay. So what's the benefit of doing this conversion into matrix product states? In matrix product states, we can compute the so-called entanglement entropy, which means that if you make the system and bipartite it into two parts, the left part and the right part, you can ask what are the amount of correlations between the left part and the right part. This is the so-called von Neumann entanglement entropy measure. If you have zero entanglement entropy, it means that the left part and the right part are perfectly uncorrelated. What happens to the left is independent of what happens to the right. But if the entanglement entropy is large, it means that there's a strong correlation between the left part and the right part. And when translate this in terms of correlation in time in recurrent neural networks, it would mean that a larger entanglement entropy signifies there are long-range information propagation from the words that you have read in the far past and the words that you're gonna read later, and then that will affect your prediction of the sentiment analysis. But if your entanglement entropy is low, it means that your sentiment analysis task will not care too much about what you have read in the far past, meaning that you only look for certain things in this review, and then you can already classify it well enough. So it's a good measure that allows you to look into correlation in times of recurrent neural networks of the recurrent arithmetic type. Okay, so let's try to apply this recurrent arithmetic circuit mapping into MPS and measure the entanglement entropy when you train this recurrent arithmetic circuit on IMDb dataset, and we also tried on Rotten Tomato dataset, and they show similar characteristics. So I'll just explain what we see in IMDb dataset. So in IMDb dataset, you have a gigantic list of reviews, and then you try to ask the computer to say that from this review, is it a good or bad review? So you assign the probability 1 is if the review is good, and then close to 0 if the probability is bad. So after we have trained this recurrent arithmetic circuit by increasing the number of hidden neurons, sorry, I forgot to mention one thing. There's this terminology in physics called bond dimension. Bond dimension here you can directly translate into the number of hidden neurons in your recurrent neural networks. And in the standard practice of recurrent neural networks is that the larger the model, the better. But it's not always the case. Sometimes you exceed certain values of the number of hidden parameters, and your model doesn't get much better. This is exactly what you see here. What you're seeing here is that I'm increasing the size of your RNN, in this case, the number of hidden units. And as you increase the number of hidden units, the training and the test accuracy gets better and better, but it doesn't get better forever. It's saturated at some values. In this case, the training accuracy saturates at around 91, 92%, and the test accuracy is roughly 87%. One thing to note is that if you look into the entanglement entropy measure, remember it measures a correlation in times between the past and the present. The saturation points between the correlation in time, as well as the train and the test accuracy, somewhat saturate at the same value approximately. Um, so this tells you already that even though you increases the bond dimension or the number of hidden units, there's no more correlation you can gain from this kind of architecture. So with this simple kind of architecture, you can get the minimal model size rather than increasing your model size forever. You can truncate at some values where the entanglement entropy is saturated, and as a result, you can get a minimal model size for this class of uh, recurrent arithmetic circuit for sentiment analysis. Okay, also, I haven't told you that word embedding is extremely important. What we're seeing here is that there's saturation in the entanglement entropy, and as a result, the training and the test accuracy also saturate. Um, but this happened when we fixed the word embedding. I took word embedding from word2vec, which is the standard way that the Google team has used. However, you can also train the word embedding along with the model. So your phi will be some fully connected neural network, and you can use that to train your model at the same time. So you can train both the RNN and the embedding at the same time. By doing that, interestingly, what you are observing here is that the training accuracy increases from 91, 92% to almost 99%, and the test accuracy is now exceeding 90%, which is pretty good for this very simple architecture of neural networks. Also, interestingly, what you're seeing here is that the entanglement entropy, remember it measured the correlation in time between the past and present, drops from the case where the training accuracy was lower. Here, the correlation in time is about this order, and this when you train the word embedding, the correlation in times dropped by a factor of 2. This tells you that something must have happened to the quality of the word embedding. So if you look in the quality of the word embedding by measuring the similarity between two opposite words, you expect that if the two opposite words or the two words that have opposite meanings are measured in terms of the dot product or the similarities of the vectors, they should appear in the opposite side. So worst and best, the dot product of it should be negative, or boring and interesting, the dot product of it should be also negative. So in this case, when the entanglement entropy drops, we also see that the quality of the word embeddings gets better and better, as signified by the meaning of the two opposite words. They appear in the right locations in the word embedding space. So interestingly, what we're seeing here is that in sentiment analysis, we probably don't need a long-range correlation, because long-range correlation doesn't boost your accuracy much. But what matters more seems to be the word embedding. The quality of the word embedding plays a crucial role in boosting up the quality of your model for sentiment analysis. And this somewhat agrees with what the machine learning practitioners have observed experimentally. If you go into the website that tells you the top 20 or top 30 list of sentiment analysis models, you find that one of the best models typically have a very simple architecture, yet they use a very high quality and high dimensional word embedding in order to perform well and be in a top list. And our work has highlighted that, in fact, if you look into the correlation in time for this task, it's not very strong correlation in time. Namely, you don't need to look into the far past in order to justify whether this is a good or bad review. What you need to care more is the meaning of each word. And that probably is how our brain works as well when we try to look for a review and try to giving it a rating of good or bad, because I might just try to look for the frequency of a meaningful word. For example, good, amazing, uh, uh, terrific, or something like that. And if I see a lot of these words that are meaningful in terms of positive meaning, I would likely I would likely rate this review as a good review, right? So it's kind of agree with how I read the review myself. And it also tells that, in fact, to do it well on a computer, you can adopt the same methodology, and this entanglement analysis, entanglement entropy analysis already reveals to you that this is the case. So this tells you that, okay, sometimes you can apply tools and techniques in many-body quantum physics to shed light into the inner working of hard to be explained neural networks type model. And currently there have been many proposals to look into this kind of intersection, namely using tensor network, which is a more general types of matrix product states being applied here, to look into the correlation structure in your data and try to use entanglement entropy and other tools to build a minimal model and look into the nature of certain machine learning tasks. Okay, so that should be the end of the first part of the talk. And if there's any question, please feel free to ask before I switch gear and go to the second part of the talk. Okay, so if there's no question, we can defer to the end.
Yeah, there are no questions, Dr. Chotibut. We can continue, and if there are questions, I'll let you know.
Okay, sure. All right, so we have seen that applying tools and techniques developed in the quantum side has already been useful in terms of looking into inner working of complex neural networks type models, and it helped you build a design principle for machine learning task. On the second part of the talk, I would like to tell you the other direction, namely how can we use a useful machine learning models, in this case reservoir computing, to solve some hard to solve quantum many-body physics problem. So I'll tell you a little bit about what next generation reservoir computing is, and by starting first telling you what reservoir computing is and what next generation reservoir computing is, and then tell you that when you apply this new machine learning model in the right way, you can use it to solve some hard problems in quantum science. So the hard problems in quantum science is quantum simulations. When you have this microscopic degree of freedom of quantum particles interacting with each other, and you ask, what will the states of these particles look like far ahead into the future? What you need to do is to solve this high-dimensional matrix equation. What you need to do typically is to diagonalize this so-called Hamiltonian. Is a gigantic matrix depending that grows exponentially large with the number of particles that you have. So you have 10 particles, and the matrix size in this case would be 2 to the 10 times 2 to the 10. So with this exponential resources consumption, it's hard to simulate this time evolution of quantum dynamics exactly on a classical computer. And this is one of the reasons why quantum computer was attempted to be built in the first place, because we want to simulate this exponentially large system in the resource size using quantum computer instead of using a classical computer. On the other hand, since we don't have a quantum computer yet, there's another paradigm of time series prediction that might enable you to solve this problem of how to simulate many-body quantum dynamics problems. Namely, we forget about this exact description of how the time evolution works. You might be able to somehow use a large number of parameters, but not exponentially many parameters, way to look into the future of this quantum dynamics. In this case, I'll use the so-called next generation reservoir computing in order to skip ahead into the future of the quantum states. So given time series of 2 quantum states in the past, this model can skip into tau time step ahead without computing the intermediate time in between. And as a result, it can save computational times and know the future using a data-driven approach rather than exact parameterization or exact diagonalization of the models. Okay, so let me tell you about the machine learning model first. So in reservoir computing, basically you have a time series, and this time series can be high dimension in DI dimension, and this time series will come into a reservoir, and the state of this reservoir is updated by a recursive rule R. This state of the reservoir at the current times is from this update rule R of the current input that come in at the current step, interacting with the previous state of the reservoir. And this map R is highly nonlinear and not trainable. So you fix R. You can think of it as a fixed random neural network. You randomize a set of RNN and then you fix that weight forever. That would be one typical type of reservoir, but there are other types as well. In general, is any nonlinear map that is non-trainable and high dimension. The dimension of the reservoir state is much higher than the dimension of the input state. By these recursive rules, you can unroll this computation and see that the information of the past time series is already stored in the state of the reservoir of the current step. There are many realizations of this reservoir. Recurrent neural networks is one of the first one that are used, and there are many others that are nonlinear. Any nonlinear can be applied to do that. For example, some Kuramoto oscillator models and some mechanical properties of certain things that are nonlinear. And once you have the state of the reservoir that interact with the previous time step of the input, you read out the state of the reservoir in order to make the prediction. And the prediction is typically just a linear map, or linear regression prediction. And the output will typically be made to be the dynamics, the next time step, for example, of the input dynamics that you care to predict. Okay, so because it's a linear prediction, you only need to train a large weight matrix W, and the state of the readout of the current step, the reservoir, will be applied by W in order to give you the prediction of the dynamics that you care about. Because the output prediction time step is somewhat arbitrary, you can also predict far future states of your dynamics. In this case, rather than predicting the next time step, as in before, you predict a far ahead future state tau. So because the training, basically you try to match the values of the output with the true values. So it's a minimum regularization terms. It is like the standard training. Is a convex optimization problem. And typically W is high dimension, you need to add a regularization parameter so that it's not over parameterized. This is the typical Tikhonov regularization problem. And because it's a simple convex optimization, there's an exact value of the trained weight W that comes out from the data matrix X and the label matrix Y. So X here is just the column vectors stacked together on a column of the matrix X, and Y here is also a column of the output label associated with the corresponding X that you need to predict. Okay, so the typical prediction, you can iterate this forever, and once you have trained W, you can ask what is the next time step, and then you can keep iterating. So this is autonomous prediction. Note that because training is simple and it's only convex optimization, there's no need for backpropagation, which is very costly, especially if your reservoir is high dimension. So this is one of the key features of reservoir computing that has gained traction in time series prediction community. Okay, one of the first paper that has made this model become more famous among physicists is Edward Ott's paper when he applied reservoir computing based on recurrent neural networks to predict spatial temporal chaos, in this case, Kuramoto-Sierpinski model. The top row is the target prediction, and then this is the prediction that comes out of the trained reservoir, and the error is very small until 6 Lyapunov time. This is extremely good because the model doesn't know about the dynamical equation of Kuramoto-Sierpinski. It's just basically a nonlinear nonlinear update rules and the linear regression that learn the structure of the time series. So it's quite remarkable. On the other hand, you can also apply a quantum substrate rather than using recurrent neural networks or the classical substrate as a reservoir. People have used quantum Ising model because it's high dimension as a way to build this high dimensional mapping of the time series, and people are still exploring how to build a better quantum reservoir for a more complex time series prediction task. Okay, however, one of the disadvantage of a reservoir, even though this map R is fixed, training accuracy depending on different realization of R. People typically randomize R. For example, you randomize a weight in RNN, and if you are lucky, your prediction accuracy will be high and generalization capability is also high. But sometimes you're not so lucky, and your prediction, both accuracy and the taste, is not that high. There are some debates of whether or not you should initialize this RNN near the edge of instability. Many people have found that if you initialize R for certain data set near the edge of instability between order state and chaos, then your model will be able to perform better. But in some other data set or some other physical reservoir, it doesn't seem to suggest so. And as a result, it's still under a strong debate of whether or not you need to initialize it near the edge of instability. And there's no clear strategy of how to optimize this hyperparameter that you're not going to train, but you're going to fix it in the first place. So then came a paper in 2021 called Next Generation Reservoir Computing. So you retain all these computational steps in the reservoir. However, there's no physical reservoir here. You build a nonlinear representation from the data itself, and the memory of the past comes from this new feature map, which is the concatenation of the past time series data, in this case by m time step. So this is a direct sum, so you concatenate the data set of the previous time together to build the memory of the past. And the nonlinearities come from this tensor products of order p. In certain limits, this mapping is shown to be equivalent to a nonlinear vector autoregression, which is studied in econometrics in statistics long ago. And it has a universal approximation property for certain well-behaved dynamical systems. So in the simplest case, without having any reservoir and have the nonlinearity of order 2 and only 2 consecutive time delayed coordinate embedding, the state of the reservoir K at the current times is basically this map. So you have this nonlinearity by this quadratic nonlinearity, and you concatenate it with its own time series at a 2 consecutive time. And this is the nonlinear map that is simplest. That turns out if you apply it to a quantum system, it can do quite remarkable things. Training and prediction are the same as before because it's convex optimization. The other things that change it is how to get this map R, which no longer depends on the reservoir, but is built directly from the data, as I said earlier. So we apply this to solve a hard to simulate many-body quantum physics problem. Namely, we have the time evolution of the quantum states, and because quantum states, you need to specify what is the amplitude. In this case, it would be the complex number rather than a real number in each of the basis states. And by this dynamical history of it, we can try to predict what is the far future states of these quantum states. Okay, so we will learn this weight W from training it and use it to predict the far future states of quantum dynamics. In quantum dynamics, there are models in which is simple and models that are complicated. So I'll start with simple model. This is the model that explaining how this microscopic degree of freedom of spin interacting with each other on the nearest neighbor site, and there are some external field that tries to flip it in the both position in the both directions. So in this case, we applied it to solve the so-called transverse field Ising model in a disorder phase. What we found is that the amplitude of the bases, both the real and the imaginary parts, because of the complex numbers, agree really well between the prediction and the target values that you care about. So it works quite well. If you look at how close these two states are as a function of time, they are almost perfectly matched. And you can also measure some local, what physicists call observables, local values of the spin they kind of agree really well, even though the model in GRC doesn't know anything about this Hamiltonian or how the interaction looks like. It's purely data driven. But this is a simple model because you look at the dynamics, it looks like simple Fourier transform would be able to extract the patterns. You can also apply it to a more complicated model called tilted field Ising model in this case, and with a specific tilting angle theta. When you apply external magnetic field in certain angle, your system become chaotic in the sense that there are exponentially many Fourier frequencies that arise, and as a result, it will be difficult to do just a standard Fourier transform and use frequency fitting. And as you can see here, the model is kind of more random and has less structure. Yet the prediction agrees really well with what you need to predict the target. And this is skipping ahead also in a million step into the future. So the model only see a million time step in the past, and then you try to predict the current step, for example. And it works quite well. And the fidelity, which measures how close they are between the two states, remain relatively high, close to 100% still. So the models work really well, actually. However, there are some cons to this because you require to do matrix inversion of this gigantic matrix. And as I said earlier, in any quantum simulation, you suffer from the fact that you have exponentially large resources required to store a quantum state. Here we also have that, except that we don't need to compute intermediate time in between. We can skip into the far future state. And the cost of this matrix inversion will scale still exponentially large with the number of your particles that you have in your quantum system. So it's still not feasible when D is above 30 on my laptop. So how do we bypass this? So probably this is not the topic of my talk, but I just want to show you that there are some quantum algorithms that we have come up with that enables you to embed this matrix into a quantum circuit and allows you to train the model accordingly, and you can apply this to skip ahead into quantum dynamics, given that you can encode this dynamical states of the quantum system into a quantum circuit. And the time scale of this matrix inversion and also prediction all is scaled linearly now with the number of the particles that you have, rather than scaling exponentially large with the number of particles that you have in the classical counterpart. Okay, I might not go into the detail, but if you're interested, you can look into the quantum variant of this in GRC applied to many-body quantum dynamics prediction. And the question that we are exploring now, which we will put out a paper within the next 2 weeks on arXiv, is that rather than predicting the full quantum dynamics, experimentalists sometimes they don't care about the full quantum dynamics. Namely, they don't want to know the full quantum state. They only want to know some parts they can measure or observe. In this case, if they only measure the first spin, the question is then, can you reconstruct the spin of all particles? Which sounds like magic, but in fact, in GRC can do that, because in the past has been shown that in GRC, when applied to a classical dynamical system and you observe only partially the system, for example, you have Lorentz attractor, you observe only the z-axis of x, y, and z coordinate, you can reconstruct the whole attractor of x, y, and z rather accurately. So we apply the same idea. Rather than constructing and observing the full quantum dynamics, we only observe partial observable, in this case, one spin or some spins in your system, partial system, and you try to reconstruct the whole thing. It's kind of works well. So what I'm showing here is that if I observe only one values of the spin of one qubit, and I try to apply this to reconstruct the whole thing and skip ahead into the future as well, it works quite well, even though it's a not so trivial task. So it shows some potentials of GRC in terms of partial observation that leads to gaining more information into the full states in the future. And lastly, I would like to thank my collaborators. Apimuk is my former master's student, and he's now in Singapore to do a PhD. And then Ininat is my former postdoc and is now the faculty member in Institute for Fundamental Study in Thailand as well. And if you'd like to reach out, feel free to contact me here. We'll be happy to chat. And that's the end of my talk, and thanks for your attention. I'll be happy to take questions now.
Yeah, people can